So, before we get started with any of our knot theory, we will first need to address the question, what is a knot? So, the mathematical definition of knot that we use in our studies will not be exactly what the definition that we are used to in everyday life. So, I'll precisely define what is a knot in mathematical terms. So, the main key difference between everyday definition of knot and mathematical definition of knot is that in math we always close up the ends. So in everyday what we'll have a string and we'll tie it up in a certain way and pull the ends. But in math, a knot, we will always have to take those two ends and glue them together. It always has to be a closed loop. So I'll just give some examples. So the most basic type of knot is basically it's not knotted in any way, and for obvious reasons it is called the unknot. So unknot, and it's just what you'd expect, just a closed circle with no internal structure. Then this another very common knot. It is called the trefoil knot, and I will just draw this one. It is in everyday language an overhand knot, which is basically what you do when you're tying your shoes. It's just take this and it's basically a very basic knot, except as always we always have to close up the end. So here's the diagram for it. And now I'll just give one more example, which is also a fairly common knot. It is called the figure 8 knot, and you'll see why in a second. So it's drawn like this. Like that. And it is also a very common knot, and as you see, the ends are closed up together. So these are just examples of common knots that we use in knot theory. So now, before we get to the real stuff, I will have to do one more definition. It's a technical definition, but let's just go through it for the sake of being complete. So let me erase all these. So now we will try to understand what is a projection. So a projection is basically, what I've been drawing on the board are projections. They are not actually knots, to be exactly precise. A knot is it's an object in 3-dimensional space, not in 2-dimensional space, as in it has all 3 dimensions. Like, you draw it. It's basically you take a string and you knot it up. It's not actually a 2-dimensional object. It has all 3 dimensions. But obviously we cannot keep using strings all the time. We have to draw it on the board. And to do that, we will use a device called projection. And projection is basically what you think it is. It's just, so your knot is like, let's say right here. You keep a source of light here. You project the light onto the knot. So on this board, we will create a shadow of the knot. And the only thing we have to keep track of is if you have one strand over here and one strand over here, they project like this. We want to keep track of which one is under and which one is over, because otherwise we lose a lot of information. So for example, we draw like this to indicate over and under. And one final technical detail is that we really never want more than 2 strands going through one crossing, because otherwise you can't really tell what is the relative position of this strand and this strand. You don't know which one is over, which one is under. So we never draw like this. You'll always want to have 2 pieces of string coming in at a crossing. So that's just a projection, and now we can get to the real stuff. So the most fundamental question of knot theory is, how can we tell 2 knots apart? So hence 2 parts. If we're given, so let's say we're given one knot M in space right here, it's in this area, and we're given another knot N in this place. So we have the knots M and N, and they're in 3-dimensional space. We want to tell if we can get to if those 2 knots are the same. So I will define what I mean by the same. Basically what it means is, if you make those 2 knots by string, you keep one here, you keep one here, can you move the string around to get from here to here, but you cannot cut the string or anything like that. You have to keep the string closed, and you can just move it around. That's all you can do. So the string can't pass through itself, basically. And we say that if those 2 knots M and N can be transformed into each other, as I described, just by normal motions, but not like cutting the string or anything like that, we call those 2 knots ambient isotopic. So that is just basically a definition, because it does not tell us actually how to tell what those 2 knots are apart. So now we will get to a more precise let's just move on. So now that told us how to tell if 2 knots are the same if we are actually given them in 3-dimensional space. Now, what we actually get are projections of those knots. We are given their drawings over here. We want to tell just in 2-dimensional, just on the board, how we can get from here to here. And it's basically just wiggling around, except done over here, but this person called Reidemeister, he basically formalized this into one big theorem called Reidemeister's theorem. And I will now, and a large portion of my time will now be explaining what is this Reidemeister's theorem. So basically what Reidemeister's theorem states is that given 2 projections of the knots, they are ambient isotopic if and only if they are connected by a sequence of planar isotopies, and these things called Reidemeister moves. And we will see what these moves, Reidemeister moves and planar isotopies, are in the next part.